All right. Welcome back, everybody. I'm going to pass back your stuff from last time, including your quizzes. All right, so what I'll do is this. I'm going to pass these around as a packet. These are your schedules, right, and your bonus questions. So on the schedule, I did look at every single one of your schedules, and everyone got 100 if you turned something in, unless it was way below what I would have expected. Like, if you just put, like, that you're in class during this time and that's all you put, like nothing else, then I didn't give you full credit. That's not what I asked for. So, yeah, work, when are you going to study? That's what I wanted to know. Now, I put a check mark if I thought, hey, yeah, you look like you've got enough time for this class. I may have put a question mark. Like, here's one, it says check mark, and it says 15 hours. It looks like this person's got about 15 free hours of study time for the week, which I think is sufficient. You know, there's some in here where it was like, you know, over 30 hours of time, which is good. So I also circled when I have my office hours. So like if you're free during my office hours, I circled it so you know, hey, look, you could actually come in and get help before class. And I think out of the entire class, there was only 4 or 5 people who cannot come to my office hours. Like, they've got something going on. Okay? So, interesting stories here. There you go. And then the quizzes, since they are quizzes, I will just call your name. Crystal, please come up. Crystal E. I know it's not AV. It's Abby. Gosh. All right. Jay Resto. Katie Zamora. Cody Morrison. Remember, everyone, this is just the first quiz. It's not the end of the world if you didn't do well. I'll drop at least one quiz at the end. So, Jasmine A. Jeff Goodson. Frank. How do you say that, your last name? Okay. Michael Chacon. Kyle Schroyer. Bianca. Caitlin. Jasmine R. Daniel Espinosa Hernandez. Courtney. Mitchell. Cameron. Raphael. Jacob. This is Raphael. Cameron. Jacob. And John Buchanan. Does anybody know where you can find the answers to this quiz? I posted them, right? And I also posted the solution to the bonus, didn't I? Okay. So that's the type of thing that I won't tell you about. Just, you know, after a quiz, just go out there and look for the answers. I'll put them out there in Canvas, all right? You need a chair? How you doing, Les? You won't. I got your email, by the way. Okay. Okay, the next thing. I said that I wanted to take a quiz grade on whether or not you watched the videos, right? So here's what I'm going to do. I have 3 documents here. It says 1.5, 1.6, and 2.1. So all you have to do is just go down the list. There's 2 pages for each one. Find your IP address and write your name. Print it so I can read it, all right? 30 minutes ago. So if you watched, I don't think you can watch all 3 in 30 minutes, but if you watched one of them in the last 30 minutes, that's okay. If you had the jump drive and I gave you the files, I know there's only like 2 or 3 of you that I did that, then all you have to do is put your name on the bottom. Just write your name, and just, you know, for now, we're just going to do that today, all right? Okay. Any questions on this? Yes. It probably hasn't changed. It's probably the same. I mean, most people have dynamic IP addresses that change, but they don't change very often. Yes. You couldn't officially watch it? It took 2 hours. Where were you playing it from? Okay. Well, here's what I recommend. Again, bring a little jump drive, and let's, you know, if you're having problems streaming it at home, then I'd like to get on a jump drive. In my previous class, I did this with everyone was required to bring a jump drive in, and that's the way we did it. But, you know, it was easier in that room because I had computers all around, and everyone could go to a computer and download it right from that computer. It was a little easier. But here, I mean, if we could get like maybe one person at each table to get it on jump drive and then just distribute it to your friends. But let's get that resolved, because as of today, there is no excuse come Wednesday I couldn't watch the video. Okay, you've had a week to figure out your connection at home or to get it on the jump drive, all right? Yes. Yeah, we'll do that later, okay? All right. What's next? We're supposed to cover a couple of sections, but I wanted to entertain any questions over homework. Any homework questions over the problems that I assigned? Any questions on the actual video lectures themselves? Anything that you watched it but you still just don't quite get? Anything? Yes.
I have a question on problem number 19 on the
1.4, number 19. Is it the x plus 2 over x cubed plus 8? Yep. That one? Okay. Be happy to talk about that. So the question here is on page 44, number 19. And it is find the limit as, whoa. I don't know what happened here. Limit x approaches -2 of x plus 2 over x cubed plus 8. So what's the first thing you're supposed to do with any limit problem? Just plug in, right, and see what you get? So let me just plug in real quick and see what we get. What do we get in the top here? 0. What do we get in the bottom? 0 also. So anytime we see 0 over 0, we want to try and do some sort of algebra or some sort of trick, right? So what about the denominator? How do you, what? You get x plus 2 and x squared minus 2x plus 4. Okay, so what are you using? Does anyone know the name of that formula that we were using there? The x cubed plus 8 is what's called a sum of cubes. Sum of cubes. So you need to know how to factor that. It's kind of like difference of squares. This is a formula also. So this should turn into x plus 2, x squared minus 2x plus 4. Sum of cubes. So if you for some reason don't recall that formula, I would just go Google sum of cubes and you'll find the formula there. I don't know where all the tables in here. Yeah. Is there any way we could maybe get one of those tables, guys, and like flip it down and, or there's one right here also. Hey, you know, hold up, guys. It's all right. If someone else comes in, we might have to do that. Okay. Does that kind of do you see that now? Okay. So when you do that, you're going to be able to get the cancellation of the x plus 2 factor. So the x plus 2 cancels, and you're still left with a what on the top there? 1? Over the x squared minus 2x plus 4. And now let's go ahead and let x approach negative 2. And the numerator is 1, and the denominator goes to what? 4 plus 4 plus 4. So 12. So 1/12 is the solution. So the limit is 1/12. Is that all right? Any other questions? Yes. Same section, 27. All right, so for 27, we have limit h goes to 0 of x plus h cubed minus x cubed all divided by h. So go ahead and check that yourself. Well, I'm sure you did. You should get 0 over 0, right? So since we got 0 over 0, we're going to have to do some algebra. Anybody who did this one, what algebra did you do? So you did the x plus h times x plus h times x plus h? Okay, that's one way to do it, and I'll do it that way. That's fine. You could also see the numerator as a difference of cubes and factor it that way. But I think multiplying out the x plus h 3 times is probably okay for a lot of you. So it would turn into x cubed plus 3x squared h plus 3xh squared plus h cubed. That is what you get when you take x plus h and cube it. You get all of that. And you still have what up there? Minus x cubed. So that's this part right here. And then on the denominator, you still have h, right? So you should get some good things to happen here. In fact, you've got the x cubes kill each other off, right? X cubed take away x cubed. And now what do you have? Yeah, you factor out an h. The numerator, every term has an h. So that's good because when you factor it out, you'll be able to cancel it. So we're doing like a greatest common factor in the numerator. So when I pull an h out, I'm getting 3x squared plus 3x h plus h squared all over h. The h's cancel. And the final step now would be to do what? Let h go to 0 now. So when I let h go to 0, I'm actually going to write the next line because I'm just being thorough here. I have 3x squared plus 3xh plus h squared. After I cancel the h's, that's what I'm left with. And now that equals no limit, because I've let h go to 0. The only thing left when h goes to 0, because these two pieces are zeros now, is 3x squared, right? Does that clarify the question that you may have had? Yes? While we're here doing this problem, I want to show you something. Some of you may have seen this already, so if you have, just bear with me. What is x plus h to the 0 power? What's that equal to? It's equal to 1. I put the 1 right in the middle there, okay? What's x plus h to the first power? Just itself, right? X plus h. All right, what's x plus h squared? X squared plus 2xh plus h squared. So that's what you would get if you multiply them out FOILed, right? X plus h times x plus h. And then what's x plus h cubed? Well, that would be what I just put on the board a second ago. X cubed plus 3x squared h plus 3xh squared plus h cubed. What's x plus h to the 4th power? So that's x plus h times x plus h times x plus h, right? 4 times. Not many people know this one by heart. X squared plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the 4th. All right. I could keep going all day, okay, never stopping. The reason why is because there's a pattern. So first thing I want you to notice about these things is let's look at just the powers on x, okay, just the powers on x. Okay, what was the power up here? 0? Do I have any x's here? No. What was the power on x, on this x plus h here? 1? What was the first power that I had on the x? It was a 1, wasn't it? That was a 1 there. And what was the power on the h? A 1 also, right? Okay, look over here. X, the power here is x squared, isn't it? What did the x start with? X squared. What did the h start with? H squared. So move from left to right across here. I started x squared, then x to the first power, right? And then no x's. So you could almost say that the power on x starts at x squared and goes down, doesn't it? X squared, then x, then gone. And what about the h's? It's the opposite. There's no h's, right? There's no h, then there's one h, then it's h squared. Look at the 3rd row, or it's the 4th row. The power of 3. My x starts at cubed, then it goes squared, then it goes first power, and then there is no x, right? The h's backwards. No h, there's an h squared, there's an h cubed. So when you take an x plus h and you expand it, it starts out x, whatever the power is on the expansion, like this is 4, that's where we'll start. X4, then 3, then 2, then 1, then gone. And the h's are backwards. Y'all see that pattern? Okay, so let me try the next expansion. See if you can help me out with this. X plus h to the 5th. What should I start with? X to the 5th plus, now don't worry about the number in front. What should the power on x here be? 4th. And what about the next one over here? What should the power on x be? 3rd. And then next one, squared, then x, and then the x will be gone, right? What about the h's? No h's on that first one, right? But then an h next to the x to the 4th. Then an h squared next to this one. Then an h cubed. then an h to the fourth, and then h to the fifth. Does everyone see that pattern? Okay, now we just need to determine what we call the coefficients, the numbers. So to help you see the coefficients, I'm going to illustrate them. Here's 1, right? This was a 1 in front of both the x and the h. See the 1, 1 there? The next row was 1, 2, 1, wasn't it? 1, 2, 1. The next row was 1, 3, 3, 1. Do y'all see that? Okay, those numbers come from something called Pascal's triangle. All right? And so I'm going to just go to a quick, below this, just show you Pascal's triangle. Pascal's triangle goes like this. You start with the 1, and then each row, you have to have 1s on the ends, and each row has one more number in it than the row before it. So the first row has just the number 1. The second row has to have 2 numbers in it, but the ends always have to be 1s, so it has to be 1, 1. The third row has to have 1s on the end, but we need a number in the middle. And that number is the sum of these 2 numbers. What's 1 plus 1? 2, right? The next row has to have how many numbers in it? 4. The 2 ends are 1s. The 2 numbers that we need come from adding the 2 and the 1, and then the 2 and the 1, which gives me 3 and 3. Do y'all see how that is coming out? What would the next row be? Pascal's triangle. Pascal's triangle. So I need 1s on the end. How many numbers in between those? 3. So I get the first number from these 2, the second from these 2, the third from these 2. So it should be 4, 6, 4. The next row, I have 1s on the ends, and then we'll have what? 5, 10, 10, 5. 5, 10, 10, 5. And I could keep going, right? The next one would be 1, 6, 15, 20, 15, 6, 1. So when I come back up here, hopefully you see now that Pascal's triangle is in here, right? 4, 6, 4, 1. Do y'all see Pascal in there? So I should get here then what? 1, 5, 10, 10, 5, and then 1. So let's try one final piece then here. What's x plus h to the 6th? 1x to the 6th. Then what? Plus, careful, 6, because you're adding the 1 and the 5. So 6x to the 5th, h plus 15, x to the 4th, h squared, plus 20, x squared, h to the 4th, 6x, h to the 5th, plus h to the 6th. There, you can go show off to your friends now. Now, Pascal's triangle is one of those things in math where Pascal gets the credit for it, but the Chinese discovered it far before Pascal. So, you know, I don't know why he gets credit for it, but he does. Yeah, he didn't put the patent on it. All right, just wanted to show you that. It's going to come up later. I will say this though. Notice that, let's look at this last one, x this to the sixth. This is always this first power, right? And notice that this number is always that number also, like 5, 5, and 5, right? 4, 4, and then the coefficient is 4. 3 was the power, and then it's the coefficient. Ooh, that didn't work. But you see that? That'll come up today or tomorrow or on Wednesday. You'll see. All right. Let's get to what today is about now. We're going to do 1.5. So I'm hoping again that most of you watched the video. If you didn't, well, so I'm starting with an example. Continuity. In the little lectures that I put out there, when they discuss continuity, it basically means being able to draw it without picking up your pencil. And there were 3 types of discontinuities. Anyone remember what they are? Jump discontinuities, infinite discontinuity, and removable. Okay? Those are the 3 types of discontinuities. What about this first one right here? This is our first discontinuity. What happens there to our graph? It jumps, right? We're moving along the graph. We're moving, and then we have to pick up our pencil and then start drawing again. We have to jump from one point to the other, don't we? That's a jump discontinuity. All right, where's the next discontinuity? At this asymptote, right? Because if we're trying to draw, what happens? Our function goes up to infinity, right? And then on the other side, if we were trying to draw, it would go down to infinity. So there's no way to draw this without stopping and then starting it on the other side. But it's different than a jump discontinuity because what? Where's our function headed? To infinity. So we call those infinite discontinuities because your function is going to infinity. Do y'all see the difference between the jump and the infinite? Okay, and then where's another discontinuity? I didn't label like 1, 2, 3, 4 for my x values. Where's my next discontinuity? At x equals 1, right? And what type of discontinuity is this? A jump again, right? So that's a jump discontinuity. Any other discontinuities? At x is 3. And what type of discontinuity is that? Removable. And it's removable because removable means that we could fix it real easily by just filling it in, filling in the dot, and then you would be able to draw it without picking up your pencil. But this question is not asking for you to do what I just asked you. It's saying to state the intervals where the function is continuous. That means tell me where the function behaves well, where you don't have to pick up your pencil. So where does it behave well? How about over here? Is our function behaving well over here? Yes. Until I get to where? X equals -3. Then I have a problem, right? But after -3, I'm good until I get to what x value? -1. So let me try and start writing this out in interval notation. From -infinity to -3, I'm good, right? And remember, these are our x values that I'm writing. And then from where? -1 to -3, right? In between there. So the way I'd write this is -3 to -1. I have to write it from left to right. And what do we put in between intervals? Union. So far, does anyone have any questions on this part? I mean, I'm not done yet, but. So I have a discontinuity at -1, but what happens right after -1? My graph is nice and smooth, isn't it? Until I get to where? 1. So I should put union again from -1. Now, What do I put here? 1 with a bracket. Why do I put a bracket? Because it includes that point. And what, let's see who really took good notes and understands this. At -1, we would say this function is what? Do you remember talking about me talking about left continuous and right continuous? As you come into -1, right? As you come in this way, it is continuous because it's nice and smooth till you get to 1, right? But if you try and go to the right of 1, it's no good, right? It jumps. But to the left of 1, it's okay. So this would be called left continuous at 1. So if you're standing at this point, 1, right there, and you look to the left of it, your graph is nice and smooth. If you look to the right, it's no good. You have to jump. So that's why you include the bracket on the -1, because it's left continuous there. Now, where does the graph pick up and start acting good again? Union from 1 parenthesis to 3, bracket or parenthesis? Parenthesis, because it's undefined there. Union 3 to infinity. So on all of those intervals, our function is continuous. Questions? It's an infinite discontinuity, yep. And all that you need for that is for your function to be heading off to infinity at that point. All right, this next example is kind of neat. Find A and B. Well, what type of function is this? When you have a function that's like different piecewise, right? It says we need to try and find an A and a B. That means 2 numbers. So A and B right here, those are constants. Give me the 2 numbers so that when you figure those numbers out, replace the A here with whatever you figure it out to be, and the B here, and that B here and the A here, that when you do all that, this entire function is continuous everywhere, from -infinity to infinity. So I'll give you a second to jot this down. Everyone has their notes, right? You should have them. Where are mine? I want to refer real quick in the notes to, I'm sorry, the notes were out of order. 1.6 was before 1.5. Did y'all notice? That's because last semester I did 1.6 before 1.5. I forgot to change it. Continuity, it's 1.5.2. Wait, no, 1. 1.5.1 is the definition of continuity. Or just because I'm going to refer to that in a second. So, everyone have this written down? Okay. Let's just look at these pieces. This first piece right here, x squared minus 4. If I graph that, it looks like a what? It's a parabola, okay? It's a parabola. It opens up, doesn't it? It's moved down 4. But it's only drawn to the left of 1, isn't it? And then the second piece is what? What type of function is that? Ax squared plus 4b. It's a parabola. Well, we don't know. Yeah, we don't know anything about a and b, do we? So I can't tell you right now if that opens up or down. But I can tell you it's a parabola, right? Because it'll be x squared, some number in front of x squared, and then some number. added to it. So that's a parabola also. And then what's the last one? What type of function is this? It's a line. But it's only drawn to the right of 4. So I'm curious how many of you really understand what's going on here. So I have a picture that will hopefully help us. All right. What I've done is I've written a little code here to plot the first function in blue. That's the x squared plus 4, or minus 4, right? Was it minus 4? Okay. There's x squared minus 4, and notice it's only drawn to the left of 1, right? And it has an open circle here. Why does it have an open circle? Go back up to the definition here. It's x squared minus 4 if x is less than 1, right? So at 1, it's not this function, right? Now, in between 1 and 4, it's this parabola, this red one, right? But we don't know what a and b are, right? So this little thing allows me to slide around and change values of a and b. So I can change what that red parabola looks like. See, so I'm changing a, and it's changing that middle parabola, isn't it? But it's also changing this black piece. What's that black piece? That's the line. It's changing the line because, look, the a here affects that line. So if I change a in this second one, it's going to change the third one. If I change b, it's going to change them both also, right? So now here's my little slider for b. If I change b, it starts moving them around. What am I trying to find? I mean, like, tell me kind of in words what I'm trying to figure out here. Yeah, but say it again. Yeah, I'm trying to connect them all. I'm trying to find an A and a B, which makes it where I can draw this without picking up my pencil. So it's continuous. I mean, this blue one's continuous, isn't it? Until I get here, and then I have a jump discontinuity. And this red one's continuous by itself, but then I have a jump discontinuity. There might be an A and a B that I can get to kind of, I don't know, maybe there's some place in here. Shit, I don't know if I'm going to be able to find it. Maybe I can. See, I can't guess. It's too hard to guess. Oh, wait, hold on, I'm getting close. Oh, shit. Every time I try and move one, it messes the other one up. You see that? But is there a solution? Well, if I click this snap, it takes us to the solution. Negative 3/16 for A and negative 45/64 for B. That's the solution. Now, how are we going to find that? Right? That's the question. But I want you to see in pictures what we're trying to do. Does everyone agree that picture is continuous? Okay. So let's get back to the problem. The key to getting started here is to understand that each of these three pieces by themselves are all continuous because they're all polynomials. And if you look at note, where is it? 1.5.9. It says functions which are continuous. All polynomials functions are continuous on negative infinity to infinity. 1.5.9. All polynomial functions. And so each of these three pieces are all polynomials, aren't they? So I know by themselves they're continuous. The problem, the only problem I have is where they come together, right? Where they join. So what I need in order to start this problem, I need f, this function, to be continuous where? I mean, I know I need it everywhere, but where are the only places I'm really concerned about? Where the jumps are, right? At 1 and at 4, right? So I need this f to be continuous at x equals 1, and I need it to be continuous at x equals 4. Does everyone understand that reasoning? It's coming from where our piecewise function splits. This is everything to the left of 1, everything between 1 and 4, everything to the right of 4. Follow? All right, so now using the definition of what it means to be continuous, let's try and figure this out. To be continuous, I'm just going to put cont dot at x equals 1 means, by the definition of continuity, so I'm referring to 1.5.1, the definition of continuity says a function is said to be continuous at x equals a if the limit as x approaches a, but what's a here? What is it? Where do I want it to be continuous? At 1? So I need the limit as I approach 1 of the function to be equal to what? F of a. What's a, though? Oh, don't confuse it with the a in the problem. Yeah, it's 1. I can see where that could be confusing. This is big time. You got to understand that. All I'm doing right there is writing down what it means for a function to be continuous at a point x equals 1. So let's work with this equation. Let's work with left side and right side. So let's talk about the left side a little bit. Well, you know what? Let's do the right side. The right side's easier. What's f of 1, everyone? So go look at your function and try and plug 1 in. So which of these pieces would you plug into? The first, second, or third piece? If I'm trying to plug 1 in for x. Well, I use this first one if the x I'm plugging in is smaller than 1. What am I trying to plug in? 1. So I don't use this piece because 1 isn't smaller than 1. The middle one, right? So if x is 1 right there in the middle, then 1 is definitely bigger than or equal to 1, isn't it? So I would use this middle piece. So go into the middle piece and replace x with 1 and tell me what you would get. A times 1, which is just a, plus 4b. Yes? So this right side of this equation was a plus 4b. Now let's go to the other side, the left side. Tell me a little bit about this. It's a limit, right? Does the limit mean that I want to plug in 1? It means I want to get close to 1, right? So if I go back up to my function, which of these pieces do I want to use? The top one, or the middle one, or the last one? If I want to be close to 1 but not 1, the top one. Because in the top one, if I plug in a number here, I can get really close to 1 without being 1, like 0.999, right? So plug in, just substitute 1 into this now, because it's a limit, right? So watch, I'm actually going to write this down. I'm actually doing the limit as x approaches 1 of the top function, which was x squared minus 4. And what is that limit? That's a direct substitution limit, isn't it? What do you get when you plug 1 into that? -3. So the left side of this equation is -3. The right side is a plus 4b. So what I've created here is an equation. The problem with that equation is that I cannot solve it. Why? 2 variables. 1 equation, 2 variables. You cannot solve and give me an answer like a equals 2. You can't, because you don't know what b is. So where do you think we're going to get the other information from? What's the other thing I'm supposed to be able to determine here? Yep. Hold on, I forgot how to go full screen here. F11. All right, there we go. So I also needed this to be continuous at 4. Does everyone see that I didn't have enough information by just looking at the continuity at 1? I need now to look at the continuity at 4 also. What does it mean? It means that I need the limit as x approaches what this time? 4 of the function f of x to be equal to f of 4. So we'll look at the left and right hand side separately. And we'll work them down left and right side. So the right side's easier, isn't it? Because there you just have to plug in 4. So I've got to go back up to my function and take a look at it. Sorry. Oh, I should get, there we go. So where do I plug in? If I actually want to plug 4 in, first, second, or third equation there, or first, or second, or third function? Third one, because I've got greater than or equal to, right? So what am I plugging in for x there? 4, plug 4 in, and what would you get? 8b plus a. Now, the other side of the equation needs to be a limit, which means I need to be approaching 4, but not 4. So which function should I use, first, second, or third? The second one. Because if x is smaller than 4, that means it's close to 4. So I'm going to use that middle one in my limit. So I'm doing limit x approaches 4 of ax squared plus 4b. And go ahead and take that limit. That's a direct substitution. Replace x with 4, and you should get what? 16a plus 4b equals 8b plus a. That's your second equation. What's that? Can do what? Yeah, clean it up. I'm going to clean it up right now. But before I get to that, does everyone see we have 2 equations now? And we have 2 unknowns. 2 equations with 2 unknowns is called a system of linear equations. And so now we have to solve the system of equations. So I'm going to make some room here. And I think I'll write the first equation here. I'm going to write it as a plus 4b equals negative 3. And the other equation, I'm going to move everything to the left side. So I'm going to subtract an a, which gives me 15a. I'm going to subtract an 8b, which gives me a minus 4b equals 0. Does everyone agree that's the second equation? Just move everything over to the left side. And I'm going to put that underneath this one. 15a minus 4b equals 0. And I'm going to put a big brace in front of this because in college algebra, that's usually the way we represent systems of equations. And now you have to solve that system. So does anybody know the common 2 methods used for solving systems of equations? That's called elimination. Elimination. And then the other one is called substitution. So it's your choice. I don't care what you do. All right? I just expect that you'd be able to solve this. So I think I'm going to do it by substitution. Actually, I did this earlier and I did it by elimination, but I'm just going to do it for substitution just for fun. Okay, so what I'm going to do is I'm going to take the first equation. I'm going to solve it for a. Why did I solve it for a? Because a, it's by itself. It's easy to get a by itself. And now what do I do with that answer? I take into the second equation, I replace a with that. So 15 times negative 3 minus 4b minus 4b should equal 0. Does everyone see? All I did was I took the a here, replaced it right there. Now, that equation only has one variable in it, doesn't it? So I get, what, negative 45 minus, what's that, 60b minus 4b equals 0. So negative 64b equals 45, and B equals negative 45 over 64. So that was a linear equation. I would expect you could solve that. So I know what B is. What do I do once I know B? I go back up to my equation with A, and I write negative 3 minus 4 times B, but B was negative 45 over 64. And I'd multiply that all out and get a common denominator, and you get A is equal to negative 3 over 16. And that should match up with what we had here. Negative 45 over 64, negative 3 over 16. Okay? There's no way in the world you would be able to get that, those two numbers, without using the definition of the limit. There's no one in this class going to be able to look at that and go, oh yeah, it's obvious. A is negative 3 over 16 and B is negative 45 over 64. Just not going to happen. Okay? So in your work on a test or a quiz or something, you know, I'm going to want to see these two limits set up the way I set them up. You know, show me the breakdown, and then from that create your two equations and then your system and then solve it. All right. All right, the last problem out of this section was this one right here. Show that this, I may have just brought my computer to its knees here. I really don't know what's going on with this computer this semester. It's really lagging on me. Yeah. I don't have several minutes. I know, but I didn't have this problem last semester, so. All right, so if you watch the video, then you know that the last example I did where is it? It's 1.5. Was this one right here. The intermediate value theorem is what I talked about. And we were going to look at this cosine x equals x and use the intermediate value theorem to show that this equation has a solution. So there's the graph of a function. And we're trying to figure out, show that there's an x-intercept here. So let me talk about the intermediate value theorem real quick. How many of you saw this on the intermediate value theorem? Eh? Make sense or no? Okay. So intermediate value theorem says this. If you've got a continuous function, which is this a continuous function? Okay. If you have a continuous function and you look at it on a closed interval, so you take it and you chop off the ends and you make it just go from one point to another. And you then make sure that the two endpoints are not the same value. So this one, you plug in a number, you get negative 12. You plug in this one over here, 5, you get 13. So you've got a continuous function on a closed interval, and the two endpoints are not the same. Then the intermediate value theorem says that I can choose any value I want on the y-axis between these two, between 13 and negative 12. Pick anything I want. Pick anything. Doesn't matter. And what is guaranteed? If I pick a value like 6, what am I guaranteed by the intermediate value theorem? At least one x value will achieve the value of 6. somewhere my graph must be 6. And it comes from an x value of 4.57. This is my, hold on, I got to make sure I got the, there exists a C. Yes, the C is the x value. The D is the y value. So it's the order of the way you do this. I pick any y value I want between -12 and 13. So let me pick this one right here. By the intermediate value theorem, there's got to be a place, some x value, that would give me that point. When does the intermediate value theorem break down? When the function's not continuous. When you have a jump discontinuity like this, because if I try and pick a value right there, there's no part of my function that ever hits that value. But that function's not continuous, right? Okay. That's what the intermediate value theorem said. Now let's see how we're going to use that to look at this question here. Show me that this equation has a solution, but don't tell me what the solution is. Just tell me it has a solution between 0 and 1. Let me go back to my notes. So I'm going to write down the equation. The equation is cosine x equals x. And I want to look at it on the interval 0, 1. There's some number between 0 and 1 that I should be able to plug in that makes that true. So here's the way we approach it. We first of all take everything to one side of the equation. And then I look at the left side of the equation as a function. And I call it f of x. And so what I'm asking for here is to find when f of x is 0. What do those correspond to geometrically? Like, if I ever tell you, hey, set a function equal to 0, what are you actually finding geometrically? When the function is 0 is what on its graph? The x-intercepts, right? This corresponds to the x-intercepts, doesn't it? The x-intercepts of the function. So looking at the function, f of x equals cosine x minus x on the interval 0, 1. Let's look at that function and see if we can figure out if it ever achieves 0. Tell me about this function. Is it continuous or not? Is this function continuous? Can you draw that function without picking up your pencil? Yes? Why? Because 1.5.9, the theorem, 1.5.9, says what? All polynomial functions are continuous. Isn't x by itself right there? Isn't that a polynomial? And what is cosine x? A trig. Doesn't it say all trig functions are continuous? Yes? And look at theorem 1.5.8, the one right above it. Look at number 1. What does it say? F plus g is continuous. So if you take two continuous functions and you add or subtract them, you're still a continuous function. Do y'all see the combination of the two theorems there? So I know right away, right now, f is continuous on 0, 1. In fact, it's continuous everywhere, but I only need it to be continuous on 0, 1. So all I need to do now is plug in 0 into that function and 1 into that function and see what happens. What do you get when you plug 0 in? What's cosine of 0, everyone? 1 minus, plug in 0 for x, you get 1, don't you? What's cosine of 1? Well, you probably need your calculator for that. Minus 1. Make sure you're in radian mode on your calculator when you do cosine of 1, and then subtract 1. If you're in degree mode, it's not correct. So what do you get? It's cosine 1 minus 1? Negative 0.45? Close enough. Anyone else get that? Yes? Okay. So look at what this is saying. I mean, this is the fundamental part of this. Let me bring this picture back up. We're looking at the interval 0 to 1, right? We evaluated at 0 and got 1, right? We evaluated at 1 and got negative 0.46 or 0.45. And this is a continuous function, which means I have to be able to draw it without picking up my pencil. Why can you guarantee me an x-intercept now? Feel like I'm losing touch with all of you. Yes, the intermediate value theorem tells me that, but just in kind of, you're like trying to explain this to someone who's not in calculus, like, look at this picture, tell me why I have to have an x-intercept. I've got a y value that's positive, right? And I've got a y value that's negative. The two ends, one of them is positive, one of them is negative. And you have to draw a curve connecting those two, right? And you're not allowed to pick up your pencil. So if you've got to go from a positive number to a negative number, you have to pass through what? The x-axis. You must cross 0, don't you? So that function must achieve 0 somewhere. And therefore, it has to have an x-intercept, and therefore that solution to that equation must exist. So when you're trying to explain this on a test or a quiz, all you're trying to show me is that there's a change in sign. Therefore, 3 dots like that in mathematics means therefore. That's a shorthand for writing the word therefore. Therefore, f of x, the function, and I've got to get this figured out. F of x equals 0 somewhere in the interval 0, 1. Which means, what was f of x? Cosine x minus x equals 0. Somewhere in there, right? Somewhere in there. Which means that cosine x equals x, moving the x to the other side, somewhere in there. Which means there's a solution somewhere in there. Does it tell me what it is? Does it tell me what the answer is? Do I know the answer? No. But I know it exists. I know somewhere between 0 and 1, the answer exists. Yes, you're showing existence of a solution within a range from 0 to 1. And you may be sitting there going, well, who freaking cares? You show me there's an answer, but who cares, right? You're not telling me what the answer is, and I'll explain why this is important in a second. But do you understand the logic here? The first thing you have to have is what, though? You have to have what before you can even begin this problem? I mean, the equation, but after that, what's the first thing that we showed? Continuous. You've got to say first the function's continuous, because the continuity is what forces you to draw between the 2 points without picking up your pencil. So the continuity right there said, let's draw without picking up our pencil. Then these two things showed us we had a change in sign, and therefore we know we had to pass through 0. Yes? Okay.
So as far as like a written
it would be your work. It would be, you would say, you know, the f of 0, the f of 1, show change in sign, and then your conclusion. So there's not like a lot of work for this. What's more important, I think, is for you to understand what's happening here, all right? Now, where's the value of this? Like, how in the hell does this work? So how many of you have a pretty good background as far as your calculators are concerned? Like, you feel pretty comfortable. Could solve an equation. Can you solve an equation on your calculator? How many? Anyone here think so? Can you try and have your calculator solve cosine x equals x? Whoever has a calculator. And if you have one of these fancy graphing calculators and you don't know how to solve the equation cosine x equals x, then it's just table candy. That's all it is. It's just to look good. You got this thing. You should try and learn how to use this. Solve an equation with it. Hey, I had to teach myself. It's not easy reading the manuals on this stuff, but you know. Okay, anyone got it yet? No? Yes? You got something? What do you get? Are you in radian mode? You are? What in the world is going on with this thing? Guess I can't solve anything because this damn thing won't work. Oh, my key was stuck. Okay, mine's working right now. Anyone else? You got 3 point something? Point something? Okay. And my calculator's like, I got 0.739. Anyone else get 0.739? No? That's what it's supposed to be. All right, well, I don't want to take too much of your time doing that, but let me try and get to the point of why this, what we just did, is important. How in the hell did my calculator just solve that equation? There is no algebraic way to do it. Look, if you take this equation right now and you try and do this by hand, you are not going to be able to solve this equation. It's impossible to do that algebraically. The problem is that your x, if you're trying to solve for x, on the left side, your x is trapped in the cosine, isn't it? On the right side, you've got x, but you need x by itself, or you can factor it or something. So the only way to release the x from the cosine is to come in with arc cosine on both sides. But when you do that, you have to do it on both sides. So now you actually release the x on the left side, but now what have you done on the right side? You've trapped it with the arc cosine. And so again, you're stuck in this loop where it's really algebraically impossible to do it. So, but how did your calculator do it? Your calculator can only do what? I mean, what's the only thing that a computer knows? Right? Every computer in the world only knows this and this. On, off. Electrical signals there, not there. There, not there, right? That's all a computer knows. Zeros and ones, binary. So does it sit there and go, cosine x equals x? Let me figure this out. The only thing your computer can do is arithmetic, addition, multiplication, right? But it can do it fast, can it? Your computer can add and subtract and multiply and divide so quick. I mean, it's mind-boggling, right, how fast it is. So here's what your computer does to solve this equation. It starts out with 2 points. And just for simplicity's sake, it starts out with 2 points, 0 and 1. Now, your computer can very easily figure out what cosine of 0 minus 0 is, right? And it would come out with an answer of 1, wouldn't it? That's what we got also. And then it would plug in 1, and it would get, what did we get, like negative 0.46? So your computer knows the same thing you knew. The answer is in there somewhere. So what it does is what's called, anyone who's going to be a computer science major at some point will learn this, is called the bisection method. And so what your computer does is it bisects this interval, it cuts it in half, and it looks at 1/2. Okay? So now what your computer does is it plugs in 1/2. And if you plug 1/2 in, it will come out to be a positive number. So what does your computer now know? It's on the right side. See, because your computer goes, I can test this is positive. I can test this is positive. No change in sign. Therefore, must be here because this goes from positive to negative, right? So what do you think it does now? It bisects that and does 3/4. What did I say the answer was? 0.73? And it'll turn out that it will be, if your computer does it, it'll be negative here. So what does your computer know now? It's in between where and where? 1/2 and 3/4. So what does it do? It bisects again. Now it's doing this like in nanoseconds, right? I mean, it does another test there. And that one would test out to be positive. And then it bisects again. And it keeps doing that until the interval gets to a certain predetermined tolerance. Let's say 1/1,000,000th. The 2 points are within 1/1,000,000th of each other. And then it says, take the average of those two numbers, that's the answer. And it spits it out an answer. It gets as close as a pre-built, predetermined. Yeah, I mean, you can keep cutting the interval in half. But at some point, your points are so close together that the number of decimals between them is past what this computer's tolerance is set for. Yeah, I mean, it's just what the code is. Now, that method is the most primitive method for solving an equation by a computer, the bisection method. There are other methods that are more efficient than this. And the book even goes through one. And if you take any courses on numerical analysis, this is what you learn, is other methods to do things like this, solve equations. So, but this is all based on the intermediate value theorem. Yeah, I mean, with any real-world physical problem, you can only get within a certain tolerance no matter what. You know, if you're building a, I don't know, a car, right? You can put the alternator in there, and you know, there's a little wiggle room, and right, you're building an aircraft. I mean, you got to have tolerances, or got to be, yeah. So anyway, I'm just trying to get you to see that your calculator doesn't know anything you don't know. It just works a lot faster than we do. Okay. All righty. Well, I'm done with this section. I believe I'm done. Yeah. And I put this up earlier. The problems for 1.5 were given last class, weren't they? Okay. So I'm ready to move into 1.6. I used the solve feature on my calculator, but it depends on your calculator. I think your calculator is a TI-84, 85, 83. Yeah, I mean, I'd have to look at each of your calculators. You might have a numeric solver feature. Yeah, don't worry about it now. Okay, 1.6. So I'm going to look at the notes right now for 1.6. Remember, these were out of order. And this is the section on limits involving infinity. This is a pretty tough section right here. There's a lot going on. The two ideas in this section are as follows. And since there's two ideas, I'm going to show you both side by side. On the left side, I'm going to look at a function that does something like this. And I'm going to put, let's say, x equals 1, y equals 1, dotted line. That's like a horizontal asymptote. So where is that function on the left side headed as x goes to infinity? As x goes to infinity, doesn't that mean to the right forever? So if I start going like out the right side like this, where's the function headed? What is its value headed towards? It's approaching 1, isn't it? It's approaching 1, and this is the y value, right? So here, x was going to infinity, the function was going to 1, right? X was going out to the right forever, the function was headed towards a number. Does it ever necessarily get to that number? No. Okay. Compare that to this function. Let's say that's the number 1 there. Here, I think I'll draw the function on the other side also, like that. On the graph on the right side, as x goes to 1, where does the function go to? The function goes to infinity. Those are completely different concepts, aren't they? The one on the left, what part of it's going to infinity? The x, and the function goes to a value. The one on the right, the x goes to a value, right? 1, and the function's going to infinity. Right? Okay. We're going to investigate both of these things today. That's what this section is about. Looking at these two scenarios. So the first thing that we should note, and this is 1.6.10. It says that if you have limit and you want to see what happens as x goes to infinity of 1 over x to the n, you should get 0. Now this works when n is equal to 1, 2, 3, 4, any positive integer. This is a big formula you should remember. But I don't want you to remember it like that as a formula. I want you to remember it more conceptually. I want you to look at it like if in a limit you have the form of a fixed number over something that's becoming infinite. So look at that limit up there had 1 over x to the n, right? 1 over x to the n. 1 on top is a fixed number. The bottom, though, x is getting bigger and bigger and bigger, isn't it? So anytime you have a number on top that's not moving over a number that gets bigger, what happens to that ratio? It goes to 0. It gets smaller, right? That's one of those concepts that everyone here needs to understand. And you can give yourself an example next to it, like 3 over 10, 3 over 100, 3 over 1,000, 3 over 10,000. Look at those numbers. That sequence of numbers is getting what? Bigger or smaller? Smaller. It's getting closer to 0, isn't it? The numerator is staying the same, but the denominator is getting bigger. Anytime that happens, it goes to 0. And it also turns out that it doesn't matter if it's positive or negative on the top or the bottom, okay? If you had a negative 3 over something becoming infinite, it would still go to 0. So that's the one I think you should think, be able to think clearly about, something like that. So let's look at our first example, and we'll apply that. We'll see how this is all going to work out. Okay, as an example, find the limit as x approaches infinity of 3x squared plus 2x minus 5 over negative 4x squared plus 7. What are the limits that you've done, like at home and that we've done in class? What are the forms that we've seen, that we've worked with so far? Over 0, we've seen fixed over 0, haven't we? And we've seen 0 over 0, haven't we? Those are the two we've seen. Now we have something new, all right? This is the first time we've seen something like this. We're trying to let x go to infinity. Infinity is not a number, is it? Right? Infinity is an idea. It's the concept of letting x get huge. So, but we still try and do it the same way we did before. Like if we were saying let x go to 2, we try plug 2 in. Let's try and plug the idea of infinity in and look at what happens in the numerator. What do you think infinity squared would be? Yeah, have you seen that commercial? My 3-year-old loves that commercial. I don't know why. She's like, she sits there and walks around. She's like doing that thing. That little girl. Yeah, that one girl says, "What's infinity plus infinity?" And the other one says, "What's infinity times infinity?" And they all go. Turns out they're the same answer. Okay, infinity plus infinity, infinity times infinity are the same thing. It's infinity. Okay. So x squared, infinity squared is infinity times infinity, is still infinite, right? It's infinitely big. Plus, well, times 3 out front. What's infinity times 3? Infinity. Plus 2 times infinity is still infinity, right? Take away 5, big freaking deal. It's infinitely big. You take away 5, it's not even slowing it down, right? It's still going. So your numerator is headed to where? Infinity. Where's your denominator headed? So let's go and plug in here. What's infinity squared? We said it was infinity, right? Times negative 4. That's negative infinity. Plus 7. Again, who cares? That's not going to slow us down. So the bottom is headed towards negative infinity. What I can tell you right now is that I'm headed towards, if I'm even headed towards anywhere, it's a negative number, right? Possibly 0, though. I could be headed towards 0 through negative numbers. But I cannot tell. So just like we said before, 0 over 0 I said was a bad thing. We needed algebra or trick, right? 0 over 0 is never 1, right? We never say that's 1. And we don't just stop and say, undefined. That's not what calculus is about. We had to do something with that. When we see infinity over infinity now, we've got to do some work. Okay? Some algebra, some trick. So we're kind of back into the same boat that we were before. Algebra, trick. Question is, what's the trick? So let me put this down here. There's a standard practice when you get infinity over infinity. I mean, a standard approach, I should say. When you get infinity over infinity like we did here, what you want to try and do is divide out the highest power of x in the denominator. So you want to look at the denominator. What's the highest power of x in the denominator? X squared, right? I want to divide out an x squared. So how would I do it? Let me show you what I'm going to do. I'm going to leave a little space in the front of this fraction here. The only way I can get rid of the x squared in the bottom is to come in here with a 1 over x squared and multiply that through. Wouldn't that get rid of the highest power of x there? But I can't just come in with 1 over x squared on the bottom. Whatever I do to the bottom, I have to do to the top, don't I? So I have to do a 1 over x squared on top also. This is the standard trick for infinity over infinity. At this point in this class, that's what we do. Later on, we'll have another way of handling this. So let's distribute through here and see what we get. And I'll take this first one kind of slow. Distributing through, I get 3x squared over x squared plus 2x over x squared. This thing's driving me crazy. Minus 5 over x squared. That's just the numerator. Over the denominator, negative 4x squared over x squared plus 7 over x squared. So everyone see that just distributing term by term? And you should get some good cancellation here. X squared should go away there and there. What will I be left with on that second term in the numerator? Just 2 over x, right? One of those x's are going to cancel. And then over on the second one here, nothing cancels. I mean, the third one, nothing cancels. And over here, nothing cancels. So I've got limit x goes to infinity 3 plus 2 over x minus 5 over x squared over negative 4 plus 7 over x squared. And now at this point, let x go to infinity. So what happens to the 3? Well, there is no x next to it, right? So it's just 3. What's 2 over x, though? What's that go to? It goes to 0. Why? Because it's a fixed number over something that gets huge, right? Fixed over infinity goes to 0, which is what I just wrote up here, right? That big box thing, fixed over infinity goes to 0. So that's going to blow up. It's going to not blow up. It's going to go to 0. It's going to vanish. The 5 over x squared is also fixed over infinity. That's going to vanish. In the denominator, the negative 4 is going to stay, and the 7 over x squared is going to vanish. So after you do the limit, you don't need to write limit anymore. It's just 3 over negative 4. So this thing is headed towards negative 0.75. Okay. I'm going to do one more and we'll take our break, okay? How about, I'm going to kind of skip here a little bit. Whoa. Limit x goes to infinity, 3x plus 1 over square root x squared plus x plus 1. All right, let's try and let x go to infinity and see what happens. So the numerator, 3 times infinity, is infinity plus 1. Infinity plus 1 is infinity, right? Divided by infinity squared plus infinity plus 1 is all infinity. Square root of infinity, still infinity. Does that make sense that that would still be infinity, square root of infinity? Now let's just try and get our heads around this. I mean, in the previous class, we saw that when you get things like 0 over 0, sometimes that, it heads towards a number. And here we're seeing that when the top and bottom try and become huge, sometimes they actually make a compromise and head to a certain number, like the previous one was negative 0.75. So does this head to a number or not? Well, the idea here was the same as the other one. Let's try to eliminate the highest power of x in the denominator. So what's the highest power of x in the denominator? X squared, right? So I need to come into the front of this, and I left some room here, with the 1 over something and a 1 over something here, right? Now I'm showing this example because it's a little tricky. That 1 over something has to be put in front of the root. You can't put it inside the root, because if you put it inside the root to start, then the top's not under a root, right? So whatever you put has to be in front of both. Then you have to multiply it through. So what happens if you try and multiply something into a square root? Here's one way to think about it. Let's say I had square root of x cubed. Isn't that the same as square root of x squared times x? And what can you do with that x squared inside of it? You can take it out as an x out in front, couldn't you? Like this? Most students are comfortable with that. What students don't usually see is how to force something back in. When you've put something on the outside of a root and you force it into a root, what happens to it? On its way in, what happens? It gets squared, right? If that was a cube root and you try and force something into a cube root, then on its way in it gets cubed. So whatever I come up with out here, that 1 over something, I have to keep in mind that when I force it into that root, it's going to get squared. So what should I use? 1 over what? X. 1 over x. Because when I force that inside, it's going to become a 1 over x squared when it goes in, as opposed to a 1 over x. Now, is it going to turn into an x squared on the top? No, because there's no square root that I have to pass through. Yes? That x squared can't come out because it's addition, not multiplication. So like over here in the problem that I did here, the reason why this x squared came out is because that's multiplication in between. If it's addition, you can't. Is that all right? All right, so let's go ahead and pass the x 1 over x through on top and bottom. What do I get in the numerator? I mean, don't let x go to infinity yet. Just tell me, algebraically, what's 3x over x? 3 plus 1 over x. Okay, in the denominator, I still have the square root, right? Some people, I've been teaching for a long time, so for some reason people will forget the square root. Like they think it goes away. It doesn't go anywhere. It's still there, square root. When that 1 over x goes in, it becomes 1 over x squared, and it passes through to all 3 terms. So what would you get down there? X squared over x squared, which would be 1, and then plus x over x squared, which is 1 over x, and then plus 1 over x squared. Remember, when that 1 over x goes in here, it becomes a 1 over x squared, and so it's got to multiply, oops, it's got to multiply times this, this, and this. All three of them get x squareds below. Now let your x go to infinity, and what happens? Vanishes, 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 because you got fixed over infinity on those, don't you? What's left? On the top, 3, bottom, square root of 1, but the square root of 1 is 1, right? So your answer is 3. So there's some algebra there involved, right? Now I'm going to let you take your break, but hold on. I know you really want to take a break. I do too. Okay, the infinity symbol. Anybody know where the infinity symbol comes from? Well, there's several different arguments as to its origin, but have you ever seen a Mobius strip? A Mobius strip, oh, son of a bitch. There we go. Okay, this is a sheet of paper, right? We could argue that this thing has two sides, right? I mean, you got the side with a little bit of writing on it. You have the side that doesn't have any writing on it. You'll see it? Now, you could argue that, yes, there is an edge along here, an edge here, and those are sides. But just generally speaking, people would say this is two-sided, correct? Okay. If you take this strip of paper and you twist one end and you put it back upon itself like this and paste it together, then this is called a Mobius strip. And this is an example of a single-sided surface. So if you take my index finger and my thumb, they are actually on the same side of this surface. So you follow the index finger around, come back, you'll be on your thumb. You come back around, you'll be back on your index finger. So there is no two sides anymore. It's all one side. So you can almost kind of see the idea of infinity here. As you walk, imagine you're a little ant, right? And you walk, you just keep walking, and keep walking. As opposed to this, where if an ant walked, there'd be bounds. Does that make sense? So that's one argument for the idea of the concept of the symbol, but that's not why I put this up here. Because that little commercial with the blowing up heads and stuff, there are two types of infinity. There's what's called countable, and there's what's called uncountable. Now, an example of countable would be all the integers. 1, 2, 3, 4, forever and ever. If I told you just start counting, right? This was another conversation I was having with a child at a Father's Day thing yesterday. And I'm trying to explain the idea of like, you can count forever, right? You can just sit there and count. There's no biggest number. You just keep going, right? That's countably infinite. What's that? About 10. Yeah. So, but there's a systematic way to pass through the numbers, right? And another example of a countable set are all the fractions. If you take every fraction on the number line, okay, look at just the numbers between 0 and 1. Okay, so I'm just looking at that interval and just the fractions. So all the fractions in here, like 1/2, here's 1/4, right? There's all these, 2/3 is in there somewhere. Well, actually, it's on the other side. But you know what I'm saying. All the fractions in there, there's a way to start at 0 and walk your way across the number line from 0 to 1, going through all the fractions like lily pads on a pond, walking across. You'll never get to the other side, though, because there's an infinite number of fractions. But you can start walking from one side to the next and never and make progress towards the other side, but never get there. Does that kind of make sense? So it's like you step off the edge, you're on a lily pad, you go to the next lily pad. Here's my little lily pads. All right? Except that there's infinitely many, but you can start counting across. Those are all countable sets. Uncountable is if you take all the numbers between 0 and 1, including irrational numbers, which are the things that are not fractions. Then you get what's called an uncountable set. And there's no way to even start to systematically count your way through. So it's kind of like if you started at 0 and said, okay, I'm going to step to the next number. Here's the lily pad, right? Here's the first lily pad. I step to the next one. Not only will you have missed lily pads, you will have missed an infinite, uncountable number of lily pads. So you try and take a step back, and you realize you just missed again another infinite, and then there's just no way to count through them. So all the numbers between 0 and 1, if everything in there is uncountable. The fractions between 0 and 1 are countable. So those are two types of infinity. And the best analogy I have of this, and I love to share this story, is, and you can use this if you'd like, next time you're, spring break or something, you're walking on the beach at 3 a.m. with someone else, maybe, and it's all dark outside, right? It's all dark outside, and the beach is on there, right? Here's the waves and stuff, and you're talking about, uncountable and countable. Then if you look up into the sky, at a dark night away from the city, you see stars all over the place, right? Everywhere you see stars. That was a shooting one, yep. So all these little red things are stars, right? And there's a bunch of them. You could almost look at those as like the fractions. They're all over the place, right? There's so many of them. You start trying to count them, and you could maybe start counting your way through the stars in the sky, right? But you're going to pass out before you get through, right? Okay, that's the fractions, countable. The black is the uncountable. Those are the irrational numbers. And those are like examples of irrational numbers: square root of 2, pi, e. You're usually taught that those are irrational, but no one ever tells you that there's so many more irrationals than there are rationals. So everyone thinks that, oh, there's only a few. It's actually the opposite. So if you just think, someone says, okay, start counting stars, you're like, sure, okay. 1, 2, 3. And then they say, start counting the black. You can start, you try start, then where do you go? It's just everywhere. It's super dense everywhere. Does that kind of make sense? Okay, I'll share one last thing, and I'll make it, I swear, less than a minute. When I was in graduate school, I used to have, how many of you are going to go to grad school? Yeah? Okay, so you'll probably find when you go to grad school, you don't really have a whole lot of time for anything else. Like socially, you're going to be doing nothing, okay, except whatever it is you're studying. And so when I would go out every once in a while, I would like to go to these clubs and dance and just like sweat out all my frustration and like confusion, right? I just go get, you know what I'm saying, right? So I would go to this club that I always go to, and if I ever had a night where maybe I met this girl or something, I always had a question that was like my standard bar question, like, this person has to know some math, or else I can't even exist right now without doing math, right? So my question used to be, if you look at the interval 0, 1 and reach in there and grab a fraction, reach in there and grab a number, what's the probability it's a fraction? That used to be my like standard, hi, how you doing question, right? And so the probability is actually 0. Like if you close your eyes, it's like being back at the beach. If you close your eyes and just point, what's the probability that you're pointing exactly at a star? it's not going to happen, all right? You're going to be pointing at black, all right? I mean, that's the idea of it. So I asked this girl one time, and she was like, she said 0, and then she came back with some other question that I was like, I knew it, and anyway, I'm still friends with her and stuff. She programs the robots that build cars. That's what she does. Very, very bright person. But I mean, it's kind of an interesting sort of, like, you never know when you're out there, you know, what you're going to run into and people and what you have common interests in. So, all right, let's take a break. I think it's time for a break. We have a lot to do still. Let's be back at 3. Okay, let's go ahead and continue. I was kind of reminded over the break that there was a bonus question that if you have, you can turn in. Anyone? Bonus question from last class? It was number 26. Okay. All right, let's keep going here with this 1.6. So here's a new problem to look at. Up to this point, we've seen infinity over infinity, or negative infinity over infinity, something like that. But look at this one. This one's a little different. Let x go to infinity. What are you going to get in this first square root here? Infinity squared plus 4 square root. What is that? Infinity. So we have something that looks like this. It's infinity, but then what? Minus infinity again, right? What's infinity minus infinity? You would think maybe 0, right? But it's not, because what you have is a number that's becoming infinitely large minus a number that's becoming infinitely large, but one of them could be getting larger faster than the other. So, you know, one might start to pull away from the other one, and there may be a difference between the two. Or it may turn out that they pull away from each other and they just stay at a common difference between each other. So you can't tell by this. And if you put 0, that's like big time wrong. This is just like 0 over 0 or infinity. We don't know. We need to do some algebra, some sort of trick. Okay? So algebra trick. And the algebra trick that I'm going to use here is something we've kind of done when we've seen square roots before. What did we do? When we had square roots before, someone said they really liked doing it last class. The conjugate, right? The conjugate. So I'm going to introduce the conjugate. What is the conjugate of that? Okay, square root x squared plus 4, what? Plus x. Now, I can't just throw that in there like that, right? You can't just say, oh, I'm going to multiply that. You can only multiply by 1, can't you? So you have to do that over itself. Now, the original part of this, which was the black part, I can look at that as all being over 1, right? What do you get when you multiply across the top, when you do your little FOIL action there? X squared plus 4 minus x squared. So I already did the cancellation and stuff. I still need to write my limit out here in the beginning. All divided by that square root x squared plus 4, but this time plus x. And those x squareds cancel, don't they? In the numerator? And we just have the 4. And then denominator, square root x squared plus 4 plus x. Now what happens if you try and let x go to infinity? On the top you get what? 4, right? 4 is a fixed number. Over, now the denominator, we've got infinity, but this time plus infinity, don't we? We don't have the minus anymore. Infinity plus infinity is infinity. Would you all agree with that? And then that means your bottom is infinite. Fixed over infinity goes where? To 0. So your answer is 0. For this particular problem, it's 0. We're not saying infinity minus infinity is 0. We're just saying for this problem, it's 0. All right, good. Any questions on this? Okay, everything that we've looked at so far, we've been able to do some algebra on, right? Let's try something that's slightly different. This is one that I did in the notes. Limit x goes to infinity. Well, let's try this. I'll change it up. Cosine 1 over x. So what happens as x goes to infinity here? What do you get inside the cosine? Where does this thing go? Where does that go? That goes to 0, right? Isn't that fixed over infinity? All right, you get 0. So the inside is going to 0. What's cosine of 0? 1. So this limit is 1. There's no problems here, right? There's no issues. We never got infinity over infinity. We never got infinity minus infinity. We never got 0 over 0. We got fixed over infinity, which was 0. Cosine of 0 is defined. Next one. Limit x goes to infinity. Cosine x over x squared. What is cosine of infinity? It's kind of weird, isn't it? I mean, you can't plug infinity in. So instead of plugging it in, just think about what does the cosine function look like. Here's a graph of the cosine. What does it look like as I go to infinity? So doesn't cosine go like this? Is the cosine function headed anywhere? Like, is it going to a specific place as I go out to the right forever? It just keeps oscillating, right? Up and down, up and down, up. So cosine of infinity is not going anywhere, right? It's not headed. It doesn't have a limit. But where's the bottom one headed? Where's the x squared on the bottom headed to? So the bottom is headed to, what's infinity squared? Infinity. So we don't have infinity over infinity here, right? We don't have fixed over infinity because cosine's changing. But what we do have is a new term we're going to use is bounded over infinity. What do I mean by bounded? I mean, there's a restriction on cosine, right? What's the biggest cosine could ever be? 1. What's the smallest it could ever be? -1. So it's kind of like, look at all your different scenarios of what could happen. What if you're at 1? What's 1 over infinity? 0. Look at -1. What would -1 over infinity be? 0 still, going fixed over 0. So in any case, the bounded part oscillates, right? But your denominator keeps getting bigger. I think it's worth looking at the graph of this. Let me see if I can throw the graph up here real quick. I'm just going to graph what was it? Cosine x over x squared? There's the graph out to 100. So what's happening is cosine, it's oscillating, right? It's oscillating, 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 but the denominator keeps getting bigger, which really makes it makes the amplitude smaller. Go back to this right here. Would you agree that that's the same as 1 over x squared times cosine x? Isn't that the same exact thing? And isn't the number a in front of cosine x back from pre-cal? Don't you when you have a cosine x, isn't a the amplitude? The number in front is the amplitude, isn't it? Well, you can look at it as like our amplitude is 1 over x squared. So our amplitude starts to get smaller as you move on. This is a great example of what you would call a dampened oscillator. Something where, like in the real world, think about like a ball bouncing, right? You drop a ball, it goes bounce, comes back up, doesn't come as high as where you let it go, right? Comes back down, comes up, down, and then up, down, and eventually, boom, it comes to rest on the ground, right? So cosine is not, by itself, is not a good representation of that, because cosine goes up, goes back down, then back up to where it came from. I mean, you know, it doesn't start to come down. Where you, if you have this function, where'd it go? There it is. Look at this one. This is a better representation of what would happen with a ball that's dropped, right? You come down, then back up, down, back, down, boom, boom. Maybe even this would be better. Watch what happens if I square the cosine. By squaring the cosine, I will get rid of the negative, or I'll create a problem. Cosine x squared. Look at that. There's a ball dropping. Boom, 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 boom. Right? That better? And if I want, I can change. Let me see if I can do this. I'm going to do the same thing, but I'm going to, what was I using in front as the amplitude on that one? What was I using? 1 over x squared, right? Let me use something that grows even faster, like e to the x. Whoa, that went too fast. That's still too fast. Wow, that's really fast. Okay, go back to this one. Actually, I'm trying to compare these two. There's something wrong, though, with the second one. Maybe x squared, cosine x squared, exponential x. Okay, I don't want to get too much more into this. You can control how fast it starts to dwindle away by controlling that amplitude function. 1 over x squared, 1 over e to the x. All right, so what we had here was what, bounded over infinity? What does bounded over infinity give us then? Bounded over infinity is now going to go where? 0, okay? So instead of having a new formula to remember, I throw this into the category that we had earlier of fixed over, where was it? Fixed over, right there? That one right there? What I do is I say, and I think I summarize this later, fixed means fixed or bounded. So anytime you have a bounded number over something that becomes infinite, it's going to go to 0. I think this will be our last example for out of the notes. Limit x goes to 0, sine x over x. Limit x goes to infinity, sine x over x. Okay. Those are two different limits, right? What's the answer to each of them? What's the form of the first limit over here? What's the form of this one? What do you get when you plug in 0? 0 over 0. What do you get over here on the second one? Sine x, sine of infinity is oscillating, isn't it? And on the bottom, infinity. So, what's that? On which? The sine, though, on top, isn't sine a bounded function? So don't you have bounded over infinity on the second one? So 0 on the second one. What's the first one? 0 over 0, but 1, thank you. That's the one from last class I said everyone needs to remember. And so there's difference, right? A lot of times students, anytime they see sine x over x, they're like, 1. He told me to remember that. But it depends on where x is going. If x is going to 0, yes, it's 1. If it's going to infinity, 0. So it all just depends. So just be careful with that. In your notes for Chapter 1, 1.6.19, I do a summary of the limit forms. So like I say, and I'll just do a quick rundown of this. I give you all these different cases. Case 1, if you get like 0 over 0, what are you supposed to do when you have a limit that goes to 0 over 0? Algebra. Okay, next one. If you have positive or negative infinity over positive or negative infinity, you're supposed to do algebra. Okay, third one. If you have your numerator is a constant, which I'll say fixed, over 0. This is going to be infinity. Actually, I don't know why I didn't put this. Infinity, negative infinity, or there was a third case. Does not exist. I don't know why I left that out of there. Remember that? Fixed over 0? There's 3 things that could happen. Infinity, negative infinity, or does not exist. Okay, look at that fourth one. This one's kind of weird. The fourth one, the numerator goes to 0, and the denominator goes to a fixed number, but not 0. Then the answer is 0. The fifth one, that's what we just did, the fifth one. If you have fixed over positive or negative infinity, doesn't matter. That goes to 0 also. The sixth one, if your numerator goes to infinity and your denominator is fixed, well, positive or negative infinity on top, this will either go to positive or negative infinity. Y'all see I did on top left there, number 6. And number 7, bounded over infinity, and it doesn't matter, positive or negative goes to 0. So that's a summary of the limit forms we've seen so far. Okay, now I'm going to do some problems out of the section that should help you with your homework. So I'm working in 1.6. Wait, 1.6, yep. I'm going to start off with page 68. Let's take a look at number 14. Limit x approaches -3 with a little negative in top right of that, x plus 2 over x plus 3. All right, this is a good problem to start with here. Somebody tell me where it's headed. What's the form we have here? Where's the numerator headed? What is it? Negative what? -1, right? The numerator's headed to -1. The denominator's headed where? 0, right? But that's what's happening, right? That's what's happening. So what we have here is a fixed number over 0. And what happens when we get fixed over 0? What are the possibilities? Positive or negative infinity, or DNE? So I've got to figure out which one it is. Do you remember how to do problems like this? I showed you last class. Draw a number line and come in. Okay, so let me start with the number line. The good news is that for this problem, here's my number line. Here's -3. I'm only going to approach it from which side? The left, because the little negative sign up here, top right, tells me I need to come in from the left. So from the left means I need to approach -3 like this. Someone give me a value that's to the left of -3 but close to it. Okay, -3.1, 0.1, 0.001. You just don't want to use -4. Okay, you want to be pretty close. And what did I say to do with that? Plug it into the limit. So what do you get on top? You plug -3.1 in. -1.1, right? Over -0.1, right? Now, I don't even care what the answer is here. What do I really care about? What the sign is. Is it positive or negative? It's a positive number. Therefore, my answer must be what? Positive infinity. And it's only because this limit is approaching from the left. If it did not have that little negative sign, what else would you have to do in this problem? Come in from the other side also. Pick a number coming in from the right side. But because I'm only looking at left, I know whatever my answer is here, it's that sign and then infinity. So my answer, I'll box it here, is infinity, positive. Questions on that? Yes. See where I highlighted yellow? If that's not there, you have to do both sides. Correct. Or if that would have been a plus, you would have had to come in on the right side. So this was a one-sided limit. We only had to check one side. All right, let's look at 16 now. Limit x approaches pi from the right, cotangent x. Well, you may not even know what cotangent of, I'm sorry? Did I say left? I said right? That's what I mean. What's up there? I should have said from the left. If I said from the right, I'm sorry. What is cotangent in terms of other trig functions that most people are comfortable with? Like, it's 1 over tangent, but in terms of sine and cosine, because those are the ones most people are comfortable with. Sine over cosine is tangent, so cotangent is cosine over sine. So this is cosine x over sine x, right? And let's try plugging in. What's cosine of pi? -1 over what's sine of pi? 0. So what we're getting here is a fixed over 0. So isn't this the same thing we just did? You're going to have to test. But this one's a little bit different. So let's just kind of mess with this a little bit here. I'm going to draw a number line. Anyone have a question right now of what we're doing? I know that there's 3 possible answers, right? Infinity, negative infinity, or does not exist. I'm going to draw my number line. I'm approaching pi, right? From the left side again. So I'm coming in over here. Ooh. What's a number bigger than pi? 3.15. Yeah, you could try that. Yeah, that's fine. You could also be super clever and think about your unit circle and think of the fact that pi is what, 180? That's pi. So what's a little bit bigger than pi? What's an angle that you know over here that's bigger than pi? In like a radian angle that's... If you look at your unit circle, 210 is 7 pi over 6. Isn't it? But hey, let's not get crazy here. We're going to plug that number in, right? It's a little bit bigger than pi. What is cosine in the third quadrant? When you're in the third quadrant, what's cosine of something in the third quadrant? What is it? It's negative, right? What's sine of something in the third quadrant? It's negative also, right? It's negative over negative. Now, if you had to get a calculator out to do this, that's fine, but I'm doing it just by understanding the unit circle. I think I said on the first day, if there's like one thing you need to know in this class, it's the unit circle, right? That's what I mean. So that tells me the answer should be what then? Positive infinity. Now on your test, okay, if you get to a question like this and you just put infinity and there's no explanation, you're not going to get credit for it. I mean, you have to have something to show me that you understand what's going on. It's not going to be like a coin flip, you know, okay, you're going to write infinity or negative infinity. Some sort of rationale behind your answer. Okay? That's what I expect to see. Yeah, I mean, yeah, I should be able to make some sort of sense. Like, I need to see that you realize it's fixed over 0. I mean, assume that understand that I need you to demonstrate to me what you know. Don't assume I know anything that you know yet, right? All right, so our answer was infinity there. I'm going to skip, let me see, where do I want to go to now? Let's look at 22 because it just looks interesting. Limit t goes to infinity. t minus t root t all over 2t to the 3 halves plus 3t minus 5. What's happening up top? T minus t, right? Something like that. But isn't that infinity minus infinity? What's infinity minus infinity? Infinity minus infinity is, I have no idea. It depends on the problem. I just don't know. It's indeterminate. I cannot determine what that is. It's not 0. Could be 0, but it could also be infinity. It could also be 2. I just don't know. Over what? Infinity times 2 plus infinity minus 5. That should all be infinity, right? I basically don't know anything of what's happening here. And it doesn't even fall into any of the forms that I had, does it? Like, this isn't infinity over infinity. This isn't fixed over infinity. This isn't fixed over 0. This is kind of like a head-scratcher one, right? So I think to begin the problem, what I'm going to do is just do some algebra on this just to try and mess with it. First, rewriting this as the power on that t square root of t. Do you agree that that's t to the 3 halves? And if you don't remember why that's true, I'll just write it over here. T root t is the same as t times t to the 1/2, which is the same as t to the first power times t to the 1/2. And then you add the exponents. 1 plus 1/2 is 3 halves. Anyone have like an instinct of what to do here? Yeah, let's try that. Like, we know the denominator is going to infinity, right? In the past, when we had infinity over infinity, we tried to come through to try and reduce the highest power on the bottom, right? So let's just try it. I mean, we could wind up, going into an abyss here, but as long as we don't break any rules, we should be all right. So what am I going to multiply top and bottom by? 1 over t to the what power? 3 halves. Shit, come on. There we go. 1 over t to the 3 halves here. And you're going to distribute that through, right? What do you get on that first one there? Top left. T over what? T to the 3 halves, which is what? What's t? T over t to the 3 halves is the same as t to the 1 minus 3 halves, which is t to the negative 1/2, which is 1 over t to the 1/2. I'm using properties of exponents here, right? Because there's a 1 on that t. Anytime you have something to a power over the same thing to a different power, you subtract powers. So I should be getting 1 over t to the 1/2 minus what? 1, right? That's second distribution through there. They just cancel each other out. T to the 3 halves over t to the 3 halves. That's 1. Over, what do we get on the bottom? 2 plus 3 over t to the 1/2, then minus 5 over t to the 3/2. I think this is going to work, because let t go to infinity now. The first one there, the the 1 over t to the 1/2, isn't that the square root of t? So isn't that the square root of infinity? That's fixed over infinity. What does fixed over infinity go to? 0, right? And then minus 1. So I'm getting something that looks like this. A minus 1 on top, and then on the bottom, the 2's still there, plus 3 over infinity, right? Fixed over infinity goes to 0, minus 5 over infinity again. So 0 again. So you get what? Negative 1/2. Y'all doing all right? I mean, you're just going to have to get your hands dirty at home with these things. I think we'll do one more. Limit x goes to infinity, x squared minus x to the 4th. Oh, you know what? This one, we'll have to do one more after this. I'm just trying to help you for your homework, but this one's not hard enough. What are you getting as you plug infinity in, though? You get what? Infinity minus infinity. So infinity minus infinity is, yep, they'll both be positive, though. No, the minus is in front, though. So the minus is, you do the x to the 4th first, that'll be positive, but then you're subtracting it. So no, we don't know, right? Anyone see it? Good. You can factor out a what? X squared. And when you do that, you'll be left with what? 1 minus x squared. Now that changes the game, because now what you're getting is, what's infinity squared? Infinity. But now instead of subtraction or addition, you have times, what does this become? 1 take away infinity, which is, what's 1 take away infinity? Negative infinity, right? The 1 has really no effect on it. If you do 1 take away an infinite number, it's going to be a negative large number. And now we have multiplication instead of addition and subtraction. So what's a huge positive number times a huge negative number? Huge negative. Negative infinity. So this one we needed to do a little factoring first. Turn the subtraction into a product. So here's the last one, I promise. What's the limit as x goes to infinity of the cube root of x minus x? So what's the cube root of infinity? Infinity still? So we are getting infinity, take away infinity again. Still don't know what that is. Do you agree with that? Do you agree with this? That the same? Can I factor that? What can I factor out of both of those? X to the 1/3. What would I be left with? X to the 2/3. Good. Because when you have the same base, you add the exponents. 1/3 plus 2/3 is 3/3. See how that one's basically the same problem that we just did, except you had to factor something out that's a little more interesting than just x squared? Okay, but it gives us the same result. Because the first one goes, cube root of infinity is infinity. Then we get 1 minus, well, that's the cube root of infinity squared, so that's infinity. So we still get infinity times negative infinity, which is negative infinity. Okay, I think we're good. I think you can handle your homework for that now, hopefully. And that does it for chapter 1. Limits and stuff. What should we do? What should we do? There's a couple of things that you have to know before I can really do anything from chapter 2. You have to have watched the video, but I mean, obviously you have to do that. But you have to know how to come up with the equation of a line if someone gives you 2 points. So I'll do a quick review of that, and then I'm going to jump into the problems. So any questions, or am I okay to go? Keep going? Questions? No? You get? Okay. 2.1. Oh, you know what? I think I already started this. Yeah. Derivative as a rate of change. Let's just see, show of hands. How many of you actually did get to see the video for 2.1? Oh, yes, that's good. Okay. So the derivative as a rate of change, someone try and, I don't know, I just want to see if anyone can kind of like summarize what this section is about, just like in words. What are we trying to do? Find tangent lines. Exactly. Good. So we're trying to take a curve like this, and we're trying to find a formula that gives you, first of all, the slope of that tangent line. And then from that, if you know the slope of a line and you know a point on the line, then you can come up with the equation of tangent line. So there's two things. There's the slope of the tangent line, and then there's the equation of the tangent line. And we need to be able to find both. Okay? And to do that, what do you have to be able to compute? The definition of the tangent line right there requires that you can do what? A secant, but what's in front of the secant that's so important that we've been doing in chapter 1? A limit, okay? In order to define the tangent line, you must be able to do a limit, which is why we spent all that time on limits, is so that we could get to this point, which is trying to find that slope of that line. And this comes back to last class where I threw the pen across the room. And I said, what's the speed, right? At that instant in time. That's equivalent to finding the slope of that tangent line. And we actually have a way of doing it now. So the formula that you're going to need, there's two formulas that you're going to need today. The first one is the slope of the tangent line can be written as limit x approaches a, f of x minus f of a over x minus a. That's one version. If you watch the video, there's two versions of this, right? The other version is this one. And did I say in the video at all which one's better? That's right. It's going to depend on the problem you're trying to solve. There is no better or worse. It's just sometimes that first formula is nicer than the other one. Sometimes the second one's better. So, but they both give you the same answer, okay? That's the most important thing. They both give you the exact same thing. They give you the slope of the tangent line at x. Or at a point, sorry, I should say, a point on the graph. So I think we can at least try and start with an example. I think just from the show of hands, we might be able to just jump right in. So let's look at something like number 2. It's page 80, number 2. It says, find the slope of the tangent line to the curve y equals x minus x cubed at the point 1, 0. And it says to do it using both methods, basically, both equations. And all we want is the slope of the tangent line. So find m tan. I think the first thing I'll do is I'll rewrite this. Instead of y equals, I'll put f of x equals. And where is it that we want the tangent line? Let's use the first definition, okay? And maybe we should label these the 1 and 2 here. Let's use that first one. In the first one, we actually need to figure out what a is in the first formula. What's a? Where is the x approaching? So where's that information going to come from? You have to look at the x value here. That's your x. So I'm trying to figure out what's happening as x gets close to 1. So let's write out the formula for it then. Using this equation up here. The slope, I don't think I can get this. I'm going to have to zoom out a little bit. The slope of the tangent line will be equal to the limit as x approaches what? 1 of f of x minus f of 1 over x minus 1. That's what I'm trying to compute. Does that make sense to everyone? Anyone have a question on where any of that came from? Okay, that equals limit x approaches 1. What is f of x? In this problem, what's f of x? X minus x cubed. Okay, what is f of 1? So that's f of x right there. Then minus, what's f of 1? Plug 1 into the function. What do you get? 0. Good. Then over what? X minus 1? Yeah? So I haven't taken a limit or anything. All I did was just plug the pieces in. So this limit becomes limit x approaches 1 of x minus x cubed over x minus 1. All we've done at this point is we've taken the given function and we've said, hey, look, the slope of the tangent line at that point is equal to this limit. Now we have to figure out what the limit is. So now we're back in chapter 1. So try and plug 1 in. What do you get? 0 over 0. Which you should. So 0 over 0 is some algebra or some trick. Anybody see what we can do? Factor out what? An x on top, which leaves me with what? 1 minus x squared? Is that right? Now what? Because you can't cancel anything yet. What is it? By 1 over x. Okay. I'm glad you mentioned that. Multiplying by 1 over x would get rid of your highest power of x, right? But that's what we did when you had infinity over infinity. Okay, we want to make sure we're pulling out the right tool for the job, right? The job is 0 over 0. We need algebra or a trick. There's something, it's right here. Trying to get that x minus 1 on the bottom to go away because that's what's causing division by 0. There you go. The 1 minus x squared is a difference of squares. This right here, 1 minus x squared, that's a difference of squares, and it factors. So you have x, and it turns into 1 plus x, 1 minus x, all over x minus 1. Does anything cancel? Be careful. Those aren't the same, are they? They're off, aren't they? They're off by 1. But that's okay. Anytime something's off by 1, we can always just factor a negative 1 out. So I think what I'll do is I'll leave the numerator alone. And in the denominator, I'm going to pull a negative 1 out and make this a negative x plus 1. I haven't changed the problem. By taking a negative 1 out of the bottom here, I haven't changed it. But what I have done is I've made it so that these two are exactly the same now. I have a 1 minus x is the same as a negative x plus 1. Y'all agree with that? Okay. Now, let x go to 1. And what do you get? Let x go to 1. 1 times 1 plus 1 over negative 1, negative 2. The slope of the tangent line is negative 2. Any questions? We're going to do the second limit definition. I'm going to show you the picture and I'm going to let y'all go. We'll probably finish a little early today. All right? So that was the first definition. Now let's use the second one. The The second definition, I'll just write it down because it's way up there. Limit h goes to 0, f of x plus h minus f of x all over h. So that's the definition we're going to use instead. If we're using this definition, though, for our tangent, the difference in this definition is in the previous one, we replaced a with 1, didn't we? A with 1. In this one, you replace x with 1. So I'm going to let x be 1, right? So let's write down limit h goes to 0. Then it becomes f of 1 plus h minus f of 1 all over h. So I think the key to this problem is remembering that in the previous one, we let a be the 1, and we left x alone. In this formula, you replace the x with the 1 and leave the h alone. I think on the right side over here, I'm going to write down what the function was because I kind of forgot. Wasn't it x minus x cubed? Okay. So what would this first part be? What is f of 1 plus h? What would you get if you plug 1 plus h into that function over there? It's going to be ugly. Yep, 1 plus h minus 1 plus h cubed. All over. Oh, wait, I forgot something. That's just the first part. Minus f of 1. But we already know what f of 1 is, right? What's f of 1? 0. All divided by h, right? Questions? All right, so all I'm doing in this next line is I'm getting rid of that blue stuff over here. And I'm going to do my 1 plus h, just drop the parentheses. And I think I'm just going to expand the 1 plus h cubed. That means I'm going to do 1 plus h times 1 plus h times 1 plus h. And I'll even use like Pascal's triangle to do it. But I'm going to do it all in my head. So 1 plus h plus, oh, whoa, no, forgot something. 1 plus 3h plus 3h squared plus h cubed. That's what that would turn out to be if you expanded it. Do y'all believe that? And notice I left that minus sign in front of everything in parentheses because I have to distribute that minus through. Go ahead, I'll let you try and clean that up a little bit. Nah. What cancels in the numerator? I mean, what do we get that goes away there? The ones, right? So the ones are gone. Why is that a good thing? Everything that's left has an h in it, and that's when I'm going to be able to pull out an h. But you could also kind of like combine some like terms together first if you wanted to. Like I have an h minus a 3h, that's a negative 2h. minus 3h squared minus h cubed all over h. Pull the h out now. You can do negative or positive. It's up to you. It doesn't matter. You'll still get the same result. By pulling out an h or a negative h, you get the h's to cancel. And then what you're left with there, you can now let h go to 0. And what do you get when you let h go to 0? They go away, right? The two terms with h's go away, and all you're left with is negative 2, which is the same answer we just got, isn't it? Which way was easier, first one or second? I think the algebra in the first one was a little easier. But they get you to the same place, so, and you should be comfortable with both. I'd like to show you the graph of this, just to get an idea of what this looks like. I'm going to use a different graphing program to graph this for you. Has anyone here ever heard of WinPlot? I don't think you can get it with Apple products. But if you Google it, if you're interested, it's free. It's kind of archaic in the sense that there's probably a lot better stuff out there, but I've been using it for a long time. So WinPlot, I want a two-dimensional plot. I want to plot the equation, what was it? X minus x cubed, right? So x minus x cubed. And I want it to be somewhat thick so I can see it. Okay, there's the graph. And I wanted to know, I'm going to put a slider in here. And the slider is going to give me the tangent at some point. So as I slide this around, you see that that line is a tangent line? See that? At every point, there's some line that kind of balances through the function. And where were we? At 1, right? Is that where we were interested in? Yeah? So I'm going to just type 1 in here and hit enter. There we go. And look at the slope right here. See it? Slope, negative 2. So the slope of that tangent line is negative 2. Got it? That's what we found, the slope. Now, we didn't find the equation of the line. We just found the slope of the line. I think that would be a good place for next class for us to pick up. We start finding equations. Where are we headed with this, though? I want you to look at the behavior of this. In college algebra, we look at things like polynomials, and we say, okay, where does it cross through the x-axis? And maybe you were one of those students in college algebra who asked, well, how do I know how low it goes? Like, what's the lowest point? Or what's the highest point? Can I find those highest and lowest points? I want you to notice something about the tangent line at the highest point. What's the slope of the tangent line at the highest point? 0. So if we can figure out where a function's derivative, which is what we just did, the slope of the tangent line is called the derivative. If we can figure out where the derivative is 0, we could find potential places that represent the highest and lowest points on our graphs. But that's beyond today. It's kind of what we're going for, but it's a major point in this class. So I'm going to let y'all go early. Are we coming back champions or no? Game 6? No? We'll see, huh? We'll see. We may cancel class on Wednesday if it goes. And I'm just kidding. I'm kidding. I can't do that. I wish I could. Oh, yeah, let me put the homework up there. Sorry. It's in the video, but there's no guarantee you'll find it. If you want to go, you can, if you've got this. This is what you're supposed to do for next class, so that's what I would expect. There's no changes in that.